Hey there, calculus students. Welcome back to another lesson. This is Mr. Bean. Getting excited here because we are down to our second to last lesson of this whole school year. Today we're going to talk again about solids of revolution, but this time we're going to have a little bit of a variation on it. Most calculus teachers teach what was in my prior lesson with 11.2 and what I'm going to show you today all in the same lesson, but I found it's a little better if we can break it up to help you with your understanding of it. So to start off, let's remember what we did last time. We had cross sections that when we had some type of figure, a three-dimensional figure, maybe sometimes it was a curve like this, it would look like a funnel, and so some three-dimension. But if we were to slice it right down the side, the cross section, be able to open it up and look at the inside of it here, would look like this, like a circle. So that's what we called a disk cross section. That's why it was considered solids of revolution, looking at disks. And we would just say, okay, well, what's the radius of that? And the radius would then be r of x, depending on what this formula for the outside of the curve is. So that's our r of x. Now, we're going to look today when the cross-section looks like this. It is a washer, where the inside, so this would be the shaded area that we're going to try and figure out. This would be a solid part of the cross-section, and it would have a gap, a little hole in the middle. In fact, it would be good if you can draw this a little bit. And what we're going to try and do then is we need to know what is the area of what I have here in red. To know that area, I am going to need to know this distance because that is what's going to get revolved. So I take the area of the outside of the figure and I subtract the area of the inside. So you see here that from the middle to the outside would be our big radius. It's our capital R of x. And then we have our little radius. We go from the middle to the inside circle, or the radius of the hole, the inside of the object. If you take the big one and subtract the little one, you get this, what I have here in black. That seems really confusing, but this black line then, what that would equal is, it would be capital R of x minus little r of x. Okay, again, that's just finding the area of a cross-section. That leads us to finding the volume. Here's the volume of a solid of revolution if you're having to use a washer, meaning that the cross-section looks like a washer instead of a solid disk. Now, if you don't know what a washer is, maybe that's because you haven't put things together from IKEA before or something like that, but a washer just looks like that. It goes through a screw or a bolt or something. Okay, so here it is. You take the big radius, the outside radius, and you square it. And then you subtract the little radius, and you square the little radius. So here's everything that I just described. If you want to get that down, you can pause this, get it all written and copied. Don't forget you have a pi here in front from A to B. I want to make a very important comment, maybe to remind you. Don't write this down, but this is what a lot of students will incorrectly do. Okay, so please don't write this down because I don't want to get this engraved in your mind, but a lot of kids do this. They take r of x, and then they subtract little r of x, and then they square that whole thing, the difference. That is not what we want to do. Okay, this is bad. No, don't do that. So the idea is you square the larger radius, and then you subtract the little radius squared. Don't square the whole quantity. Okay, that's you'll see why in our next lesson, why kids start doing this and get it all confused, so I'll try to make this clear for today. Okay, let's move on. For this first example, we're going to take this area here that's bounded by these two functions, and we're going to revolve it about the x-axis. So this is my shaded region here. We're going to find that region and then take it around the x-axis. That means we want the exact mirror image across this this point. So it's kind of like this creates the symmetrical version. So let's see if I can sketch this without being too sloppy. Something like that and something like that. Okay, so then I can kind of color that in. And then what are we going to have? We're going to have it go around in, oh, that was awful. Go around in a circle. So we create this kind of oval shape that comes around here like this. All right, let me show you what this would look like. So here's the same graph, and let's revolve it. Starts to revolve. It's kind of hard to see, so let me turn this. You see it revolving around and around, and it's coming back slowly. There we go. Whoa. And it's almost done. I can't control this thing. Whoa. Okay, so now you can see here the shape of it. It's actually a little bit, it's got this gap in here. So if we were to take a cross section of this, see where there's these different lines, that's a gap. If we took a cross section and just cut a line right through it and opened it up, there would be holes. It would look like a washer. So that is what the washer method, why we need that here. Let's go back to my notes. So what we're going to do is remember my large radius and my little radius. Let's figure out what those things are. So from the middle right here, from the middle, remember because I'm going around in a circle over and over and over. Let's figure out the large radius is going to equal, let's move this over to the side so I got plenty of room. Large radius is going to be from the middle to the outside of the object. Well, the outside is this curve, so that curve is the square root. So we're going to have the square root of x. And then my little radius is going to be the distance to the inside. So from here, from the middle, here to the inside, because we're going to take away all this gap. This is a hole that we're removing in that washer, and that's the x squared graph. So we say x squared. And now let's set up our volume. So volume is going to equal pi, don't forget your pi, from a to b. So from 0 to 1, 0 to 1 of the larger radius, which is going to be the square root of x squared, minus, and then the little radius, which is x squared, and then we square that. So we square each of the radii individually and with respect to x. All right, so now all there is just doing the calculus part of evaluating this integral.
0 to 1, so this becomes x minus x to the fourth with respect to x. So volume equals pi, and now let's integrate this. X squared over 2 minus x to the fifth over 5, and then that is from 0 to 1, so we plug in the 1 first, pi. Plug in the 1, and we get 1/2 minus 1/5 minus a 0, because of when we plug in the 0. So this is going to end up equaling 3/10 pi. I already did this one on the sides here, so I know what the answer is going to be.
3/10 pi is the answer for this one. That's the volume of this weird looking shape. Okay, from here on out, we're just going to set up the equation. So this part right here, that's what we're going to set up. We're not actually going to solve it for the rest of the notes, just to kind of save ourselves some time. We're getting practice setting up these things. So let's go on to number 2. Notice here I have the exact same shape, the exact same stuff going on. So the difference now is that I'm going to be revolving it about a different line, about the line y equals 1. So if I'm revolving it around that line, it's going to look a little bit different. So you have to create your symmetrical version of this across that line. So what's that going to look like? That is going to be something like this. There's that symmetrical, and then this symmetrical will be something like this. All right, so now let's create our little ovals shape, and we can see that this is going to be kind of going around and around in a circle like this. Let's see what it looks like on the internet. So here we go. This time we're revolving about the line y equals 1, which here is going to be right here on the screen. Oh, I need to make my window bigger. There we go. Okay, that's just to help us see it a little bit better. So let's revolve it. And we're going across that line. What's it look like? Ooh, fancy. You can see it coming around there. So there's not a full hole. You can't go all the way through it, but it's because it's closing tight. But there is a gap if we were to cut this thing in half. All right, there's our shape. So it's actually the same exact shape. It's just going the other direction. So back to our notes. We have the large radius is going to equal, and then our little radius is going to equal. We need to figure out those two things real quick. So the large radius is from the middle to the outside. Well, let's go to the original function. This one's the outside right there. So which one is that? That is x squared. So from there to there, it's not x squared. See, this is where it's a little weird. You have to think this right here is x squared from the x-axis to that graph. So what we want is, I know this is really hard. I got so many lines going on here. We want to go subtract, this whole distance is 1. That's the number 1. So we want to go the distance of 1 and then subtract x squared. That's what this is, 1 minus x squared. That'll give us this distance in blue right there. That's 1 minus x squared. And then the little one, the red one, in order for us to get this distance right there, we're going to take the number 1 and subtract that square root graph. 1 minus the square root of x. That's the radius from the middle to the inside of the object. Okay, so now we can set up our volume, and we're not going to actually evaluate this. We're going to save ourselves some time. So volume equals pi from 0 to 1 of, okay, what's our first thing we're going to do? We're going to take 1 minus x squared, because that's the large radius, and square it. Then we're going to subtract 1 minus the square root of x, and then square that, because that's the little radius, with respect to x. Okay, that's how you set it up. So that's our answer for this one, and we'll just stop right there. Okay, now for some confusion. Let's do it with respect to y. We're going to revolve it around the y-axis. So this time around, we're talking about going this direction. We're going to revolve it that way. So in order to do that, we first have to have things in terms of y. So we need to solve for x. When I take this thing and solve for x, I'm going to end up with x equals plus or minus the square root of y minus 1. When I take this and solve for x, I'm going to end up with x equals 1/2 y minus 1/2. So there's my two equations to work with. And just kind of, you need to be able to tell which one's which. There's my straight line. So we're going to take this area here. Now we're going this direction. So we're going to do it with respect to y, and we're going right across the y-axis. So we need the exact mirror image going this direction. Oh, look at that. My computer helps me make my straight lines. Okay, so we're going to revolve it all the way over to here. And then, so this is the area that's going to be shaded as well. And then it would be revolving in a circle, which I'm going to be horrible at making. Something like this. Okay, it'll be going around in a circle over and over, all over the place. Let's take a look at what this one looks like. Okay, here we have that graph. We're going to be revolving it around the y-axis. Let's see what this looks like. So it starts to spin, and let's come up here. Oh, look at that. It looks like, this one really looks like a pretty good funnel. It's going to have straight edges right down here because of that straight line, and then it's going to be curved on the outside. But as we look straight down inside of it, there's no gap here in the middle. Because, if we look at here, it was touching right there when we were revolving it. Okay, so that's the shape of what this thing looks like. Let's go back to the notes. And what are we going to set up? So we want the large radius first. So the capital R of x. What is that going to equal? And then we want the little r of x. What is that going to equal? So my capital R of x is from where I'm revolving to the outside edge. That is my R of x. My capital R, I should say. So that is straight to this curved parabola. This is the curved parabola. Now, which one is this? It's a plus or minus. This is the negative square root side. This is the positive square root side. So for x values anyway, these x values are negative, these x values are positive. So this one is the positive square root of y minus 1. And then my little radius is just to this line, and the distance, that radius is 1/2 y minus 1/2. So 1/2 y minus 1/2. My 1 is tilted for some reason. All right, set it up, and we are done. So the volume is going to equal pi from, now remember, we're doing respect to y, so I now have to think my y values. My smallest is a 1, my largest is a 5. You got to stop and think about that for a minute. Smallest is a 1, so I go 1 to 5. And then I say my big radius is the square root of y minus 1, but then I'm going to be squaring that. Minus, now I do my little radius of 1/2 y minus 1, and then you square that thing with respect to y this time, not respect to x. Now, yeah, we could clean this up, multiply it all out, combine like terms to simplify it, but we're just trying to set up the equations for this, so not too big of a deal. That one is the answer. Number 4, we're doing exactly the same thing, so I'm not going to rewrite the equations. You can kind of look back here, and we have them on number 3. But we're going to now be revolving about the line x equals -1. That's going to be right about here. So we're going to be revolving around this line. So the shape of this thing is going to look quite a bit different. Let's take a look what this one would look like. All right, here we go. So now we're going to be revolving about the line -1 right here. Let's revolve it, see what it looks like. And I'm going to go up on top of this thing, move down so you can kind of see what's happening. And now you can see as we revolve, we're going to have a gap. So it's going around. The outside still looks the same, kind of this nice smooth parabola. But now there is a gap here in the middle. There's a hole all the way through it. So, in fact, let's go this. Woo! Look from the bottom of it. Okay, so that's the shape of the thing that we've just created. Let's go back to our notes. So if I needed to draw this, I'd have to have my parabola would start here. Whoa, this is tricky because I'm trying to do it exactly symmetrical. So if I would be one away here, where would I be? I'd be, here's the point where it crosses. 1, 2, 3 away. So I go 1, 2, 3 this way. All right, so here's my curve like this. And then I'm supposed to have a straight line, pretty close to being straight. Okay, it doesn't look exactly the same, but yeah, it's close enough. So we now sketch this thing, fill it in, and now I have to put a circle on bottom, dash, 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 that's behind it, and then a kind of this big oval circle here. I'm running out of space on my writing pad, and then a circle here, something like that. Whoa, that is really bad. Okay, so we're gonna go around and around and around and around. You already saw what it looked like. So let's label our capital R of X and our little r. What's my big radius and my little radius? Oh, switch colors. There we go. So from the middle, how far is it from this point all the way to the outside of the object? Okay, so the outside of the object is from the x-axis. So whatever this curve is, and then we add 1 to it. That's the radius. So what do I have? I have the square root of y minus 1, and then that's the distance from the y-axis, and then I'm going to add an extra 1 to it, plus 1. That's the radius to the outside. Radius of the inside is the 1/2 y minus 1/2, but then we have to add the extras, because remember, we're going from here to here. This is the part right here that's the equation, and then we have to add an extra 1 to it from right here. So then plus 1. And then you could clean that up a little bit. That would equal the same thing as 1/2 y. Negative 1/2 plus 1 is just a positive 1/2. Okay, so our equation is now, the volume is going to equal pi from, it's still 1 to 5 again, just like our last problem, 1 to 5 of the larger radius, square root of y minus 1 plus 1 squared minus the little radius, which is 1/2 y plus 1/2 quantity squared with respect to y. Woo! Crazy. Okay, this last problem is exactly the same if you look back as number 2. There is no difference. What I want you to do is on the left side of your notes, I want you to write something like, I'll type this to make this a little faster. Write something like, how to shift the line of revolution to an axis. The main thing is right here, how to shift. We're going to shift this thing, and I'll show you. Now, the reason I'm going to show this is because this is how I actually used to teach it, and then I found that all the textbooks weren't teaching it this way. They were doing it the way I just showed you. But I found that for a lot of students, what I'm about to show you is actually easier. So you're going to have a choice to make. So please don't get confused by this. Just give it a chance to look at it, and then you can decide if on number 2 you want to do it the way we just did it on number 2, or if you want to do it this way on number 5. So you might also write in your notes on the side that this one is the same as number 2, so you can kind of compare the difference between them. Okay, here we go. So back on number 2, we kind of already did this with our picture and everything, but sorry, let's just do this again. We're going to do it around the line y equals 1. So graph this. There's my y equals 1. Let me speed this up. Okay, there's my shape. Now, what we're going to do is we're going to take this thing and we're going to, instead of figuring out what the radius is, we are going to think every time you revolve something, you just want to be able to revolve it around an axis. So if I were able to take this entire thing electronically, if I could just pick up this entire graph and move it down, so if I could just shift it down 1, then this line of revolution would become the x-axis. Let me say that again. This line of revolution, if I just shifted everything down 1, would become the x-axis. So the only difference would be I also have to subtract 1 from the equations. And then that would actually end up working. So my new equation, instead of saying y equals 0, I could say, oh, I'm going to cross this off and say it's going to be the x-axis. But if I do that, then I have to change my equation to y equals the square root of x minus 1. And I have to change this one to y equals x squared minus 1, because I shifted everything straight down. This also works when you're doing it with respect to y as well. If you're trying to move it to the y-axis, depending on if you're moving it right, you would add 1. If you're moving it left, you would subtract 1. Okay, so it just depends on which way you're shifting it. So now that we have that all set up, let's see what we got here. We've got my large radius, r of x, and my little radius, r of x. Oh, I'm just remembering something. Oh, man, a number 3 and 4. Okay, yes, some of you were probably shouting at me while I was doing this. This is supposed to be r of y. Darn it. I'm not going to reshoot this video just for that. R of y, that sounds like French. Au revoir. Okay, so this one was also supposed to be r of y, and this one was r of y, not r of x, because it was with respect to x. Sorry about that. That's a little thing, but we should probably be correct with our mathematical notation. Okay, but this one is r of x, not r of y. So my larger radius. Now we're pretending like this is the x-axis, right? So this is my new x-axis, because I just shifted everything down, and now I'm going to use these equations. So my distance from here to the outside edge, that big line there is to this curve, the x squared minus 1. So I'm going to say this one is x squared minus 1, and then this one is the square root of x minus 1. All right, let's set up our problem now, and we're done. Volume equals pi from, the x values don't change, still from 0 to 1, 0 to 1. But now I'm just going to take this one, my large is x squared minus 1, quantity squared, minus the square root of x, put it in parentheses, square root of x minus 1. There's my little radius squared with respect to x. Okay, so there's my answer. Now, let's look back at my other answer on number 2. So here was my answer on number 2. I'm going to copy this and bring it over, drag it down here. Now look at these. They're different. This one has x squared minus 1 squared, and this one has 1 minus x squared. The order of them is different. So how can it still work out? The reason is actually very simple. Let me scroll down here. It's because of this. If I have 3 minus 5, that equals negative 2. If I have 5 minus 3, that equals 2. They're not the same thing, are they? So you'd think, oh, it does matter which way. But no, it doesn't. Because when you square them, you're just finding the difference in squaring it. It doesn't matter what order they go in. It's still going to be a positive number. They both will be the same thing. So that's why you can either do it like we did in number 2, where you just look at the distance from here to here, or you can do it like our example number 5, and you just shift it so that if it's not the x-axis or the y-axis, you always shift it and make it become that. All right, hopefully that did not lose you too much. You might have to watch this again to kind of really fully grasp what I was talking about. But good luck on that practice and rock that mastery check, and I'll see you back in the next lesson, which will be our final lesson of calculus. All right, see you later.